Okay, so at the end of class today, we were talking about Lenz's law, and it's part of what Faraday found, but it's about the direction, and they felt that the direction was so important that they named just the direction piece its own law. And basically what it says is that an induced EMF, and therefore an induced current, always gives rise, so an induced EMF always gives rise to a current whose magnetic field opposes the original change in the field. Okay, so an induced EMF always gives rise to a current whose magnetic field will oppose the original change in the field. Okay, so let me explain. Imagine that I have a solenoid, but it's not hooked up to a battery. It's hooked up to a voltmeter instead. Okay, and it has an iron core inside of it, and I'm going to bring a magnet with its north pole facing in towards it. So in this solenoid is like, oh no, there's a big, huge, strong magnetic field coming close to us, and it doesn't like that. In Lenz's law, what we know is these things do not like change. They want to try to stop this north pole from coming close. Well, the way you can stop a north pole from coming close is by creating a north pole here to repel it. So then the question is going to be, so which way would the current have to flow for that to happen? Again, I'm using conventional current because I have my right hand available. If I want a north pole here, that means my thumb needs to be on this side, which means the current needs to flow up in the wires here, this way. Right, so out of this and into this, and it would register like a reading in the ammeter. Okay, and so that will slow down this magnet from coming in because they'll repel each other. It might even work so well that it actually begins to repel, push the magnet away. So maybe now the magnet begins to move back. Its feelings are hurt. Fine, if you don't want me. And now this guy is like, oh no, the field's getting weaker. Oh no, he's going away. And they don't like that either. So now they want to stop it from leaving. So the current will flow in such a way in this wire to try to keep the magnet from going away. It'll want to attract it, so it'll be a south pole here. So which way do I need to curl my fingers to get a south pole? The current needs to now flow this way. So now it'll be coming down in the front. Okay, down on this side and up on this side. Okay, so now imagine I bring the magnet in, the current flows one way, and then I pull it out, it flows the other way, and then I put it in again, and I can make this current alternate back and forth. And that's where we get what's known as alternating current. It is current that shifts its direction back and forth many times over the course of a small period of time. Okay? And we can do that with something that's known as an AC generator. An AC generator. Again, invented actually by Michael Faraday, and it would be, I guess, an AC electric generator. And really, all a generator is it has a magnet, a pole of a magnet here, and a pole of a magnet here. So this might be the north, and these are permanent magnets. And then inside here, there's this loop of wire. Okay? And then this loop of wire is hooked up to like a circuit or whatever. But we're gonna rotate this wire. And so what happens is we rotate the wire, it's hooked up to a circuit, but not to a power source, right? There's no power source here. There might be a voltmeter or something, but no power source. And so I crank the generator, and if we look at just this side, okay, so I'm going to turn the generator. So imagine that this side at first starts down at the bottom, and then it comes up. So it's entering the magnetic field. The magnetic field is getting stronger The field is going north to south. I have to use my left hand just because. Field is going north to south, and I'm bringing the side that I've marked in red upward. And so that means when it's here, the current is flowing this way, right? So it's going to come up, it's going to come around the top, and now it's going to go down the other side. So now it's going down the other side. My fingers still have to go north to south. Now my thumb is going in. So in that same side of the loop, the current will now be going in the opposite direction, right? So on its way up on this side, it's flowing like towards the bottom of my page, but then on its way down, it's flowing to the top. And actually, it's going to create what's known as sinusoidal current, because when it's all, and I might need to leave this for when you come back so I can demonstrate it in class, but like when it's down at the bottom, it's kind of out of the field, and so it's just beginning to cut field lines. The fields wouldn't be that strong. It would be kind of weak. But as I bring it up, it begins to flow in the direction I have indicated here, and it comes into a strong field, so it's going to get bigger. When it's at the exactly dead center of the field, it's going to be at its max. And then as I bring it up further, it's now exiting the field, so it's going to begin to get smaller. And when it's at the very top up here, if you can see 3D, it's actually going to be back at 0 because it's out of the field. And now it's going to start to go down the other side, and it's going to change direction, but get bigger as it enters the field again. It'll be its biggest when it's on this side halfway in the middle, and now I keep turning it down, and it gets smaller again. What we are creating is a sine wave. And so AC, alternating current, is sinusoidal. Okay? It goes in the form of a sine wave. So not only is it not a constant amount, it also changes direction. Okay? So what happens then, as you turn the handle, the coils cut the field, and like I just have one coil of wire here, but if we really wanted to make a generator, we would put a whole bunch of coils here, because the more coils, the more current. Okay, so as you turn the handle, the current, the coils cut the field, the current begins to flow. As you keep turning, then it will reverse directions again and again and again. If you want more current, put more coils in, turn it faster, or make the field stronger. All of those will give you more current. Okay, so this is a generator. It's actually exactly opposite to the way a motor works. A generator requires manual turning. Like we could hook this up to water coming down a fall, to a horse, to what's that called? You know, the thing you run on, treadmill, and you could put your pet hamster or something on it, and it would turn this coil. So you're taking mechanical energy and turning it into electrical. A motor takes electrical energy and uses it to do mechanical work. So this is mechanical work, creating electrical energy. And then a motor takes the electrical energy and turns it back into mechanical work. Okay, so that's a generator. What we need to look at now for a couple more minutes is AC and DC. So AC is alternating current, and try not to say AC current because then you're stuttering. So alternating current, which is current that reverses its direction many times a second, and it's sinusoidal. Okay, it reverses its direction many times a second, and it's sinusoidal. Direct current flows in the same direction steadily, meaning it doesn't change. So an alternating current does this. A direct current, it's steadily in one direction. Which one do we use in our houses? It's alternating current for the most part. Anything you plug in is using alternating current. Anything off a battery is direct current. And this is the battle that happened years ago between Tesla, who had alternating current, and Edison, who had direct current. Okay? I'm going to do one more short video because I just want to talk just a little bit more about alternating current and direct current, and then give you a little research to do.